Section 4 of Chapter 11 is over simplifying rational expressions. We've done a lot of simplifying rational expressions in earlier chapters, I believe Chapter 8, but this gets more into factoring and things of that sort. So this is the kind of thing we're looking at. If we're being asked to simplify this expression, 5 times 3 minus x over 5x. Well, the only thing that can be done here is that we can look at this and we can say, okay, well, 5 divided by 5 is 1. So what are we left with? 3 minus x over x. And that's our simplified expression. In this case, that's all we can do. Okay, what about this one? 2x squared over x times x plus 5. Well, on the top, we can look at this as 2 times x times x. And then we can see that the x's, or one of the x's on top and the x on bottom, can cancel out. So we end up with 2x over x plus 5. And that would be simplified. These x's cannot cancel out because this is addition on bottom, not multiplication. All right, what about if we wanted to simplify an expression like this? 5x plus 3 over x plus 3. All right, just like in the last one, we said the x's can't cancel out because this is addition. Here, the x's can't cancel out either. And over here, the 3's can't cancel out either, even though a lot of people would like to simplify that. But quite frankly and honestly, there's nothing that can be done here. This is a simplified expression. All right, so we're going to do some more of this. We're going to simplify this expression, and as a follow-up, we're going to answer this question: are the original and simplified expressions defined for the same values of the variable? We'll talk about that in a second. Let's concentrate on simplifying this expression first. On the bottom, 5 minus 10x, I can factor that, so let's do that. Let's take a 5 out of that expression, 5 being the greatest common factor of 5 and negative 10x. Reverse distributive property, we referred to that as in Chapter 10. Okay, so is there any simplifying that can be done here? Yes, there is. 5 goes into 15 3 times. So our simplified expression would be 3x over 1 minus 2x. So there we have it. We've simplified the expression. These two things are equivalent. However, let's answer the follow-up questions. Are the original simplified and the simplified expressions defined for the same values of the variable? Well, what we're talking about is what number, what value of x would make this an undefined expression. In other words, if you divided by 0, this expression would be undefined. So when 5 minus 10x equals 0, that expression would be undefined. So let's find out what value of x that is by solving this equation. I subtracted 5 from both sides and then divided both sides by negative 10. If x is 1/2, this original expression would be undefined. Okay, and now we'll do the same thing with the simplified expression. What value of x would make the denominator 0? So when would 1 minus 2x equal 0? Subtract 1 from both sides and divide both sides by negative 2. You can see that they both have the same value of x that would make them undefined. So they would be defined for any other value of x besides 1/2. So yes, they are defined for the same values of the variable. All right, let's simplify this expression. And then we've got the same follow-up question down here. The first thing is, can we factor each one of these? Okay, so I got a quadratic trinomial. The lead coefficient is 1. Well, how about this? This is a perfect square. So is this. Is this value in the middle 2 times the square of this times the square of this? X times 3 is 3x, doubled would be 6x. Yeah, so the top is the square of a binomial pattern, x plus 3 squared. On the bottom, I see a perfect square minus a perfect square. So that's the difference of squares, or the sum and difference pattern. So that would be 3 plus x times 3 minus x. Then I'm looking at common factors in the numerator and in the denominator. Here's x plus 3. Here's x plus 3. Those will cancel out. And we're left with x plus 3 over 3 minus x. And we have simplified the original expression. Now, moving on to the follow-up. Are the original and simplified expressions defined for the same values of the variable? So, are the values that make 9 minus x squared equal to 0 the same as the values of x that make 3 minus x equal to 0? So let's take that first denominator, 9 minus x squared, and let's solve this equation. I'm going to factor it, and then use the zero product property to say that x would have to be negative 3 or positive 3. And then I'll take 3 minus x and set that equal to 0. Subtract 3 from both sides, solve for x. And we can see here that negative 3 is a value that would make this denominator 0, but negative 3 does not make the simplified expression's denominator 0. So they are not defined for the same values of the variable. You try it. Simplify this expression and then tell me if the original and simplified expressions are defined for the same values of the variables. Okay, so I'm looking at this top expression. The lead coefficient is 1, so I want to factor it, and I want to say what factors of 3 add up to 4. And obviously, that's 3 and 1. So x plus 3 times x plus 1 would equal x squared plus 4x plus 3. On the bottom, I can factor that expression by taking the GCF out. Greatest common factor is x. And then I see some some common factors here in the numerator and the denominator that can be canceled out. So there we have simplified the expression. As far as the follow-up goes, let's take the first denominator and set it equal to 0. Let's factor that by taking the x out and then using the zero product property to say that 0 and negative 1 would make this equal to 0. So that's what would make the expression undefined. Over here, if we take the simplified expression, set that equal to 0, okay, well that's pretty obviously, we don't have to solve it really too much. We're just saying that 0 makes this expression undefined. So the fact that they don't have the same solutions or values that make them undefined, we can say no, that they're not defined for the same values of the variable. Let's throw some probability into the mix. A coin is tossed onto the large square region here. It is equally likely to land on any point of the region. Let's write a model that gives the probability that the coin lands in the triangle. Okay, so probability would be favorable outcome. So the probability that it lands in the area of the triangle over the probability that the chance that it has to land anywhere, which would be the area of the rectangle. Area of a triangle is 1/2 base times height. Area of a rectangle is, well, in this case it's a square, so side length squared. The base of this triangle is 2x minus 4. And the height of this triangle is x plus 3. And the side lengths of the triangle or the square are x plus 3 and x plus 3. X plus 3 squared. Okay, we can cancel out the x plus 3's, distribute the 1/2, and here's an expression that relates our probability. Probability that this coin flipped lands in the triangular shaded region would be x minus 2 over x plus 3. So part B asks us to evaluate this model when x equals 5. So plug 5 in for x. 5 minus 2 over 5 plus 3 would be 3 over 8. So if x equaled 5, then the probability that the coin lands in the shaded region would be 3 out of every 8 times. All right, so why don't you try and write a model of the probability for the probability that the coin lands in the square but outside of the triangle. And as a hint for you, you can subtract the area of the triangle from the area of the square to get the area of the unshaded region. Okay, so the unshaded region would be the area of the square minus the area of the triangle. To get the probability, we'll divide that by the area of the entire region. So we'll do x plus 3 squared minus the area of the triangle. 1/2 base times height. Can't cancel those out yet, guys. Don't do that because you've got subtraction here. So x plus 3 squared is x squared plus 6x plus 9. 2x minus 4 times x plus 3 is 2x squared plus 2x minus 12. I'm not going to simplify on the bottom yet. It's not necessary. I'm going to distribute this negative 1/2. So that'll give me negative x squared, negative x, and positive 6. I'm going to combine like terms on the top. The x squareds cancel out. 6x and negative x makes 5x, and 9 and 6 makes 15. I'm going to factor out the greatest common factor of 5x and 15, which is 5. And finally, I'm going to just write the x plus 3 squared as x plus 3 over x plus 3 because I can cancel out these x plus 3's. Okay, so we've got an expression that shows the probability that it lands in the square but not the shaded portion, 5 over x plus 3. Let's evaluate the model when x equals 5. So that would be 5 over 5 plus 3, which is 5 over 8. So if x equaled 5, the probability that it lands in this unshaded region would be 5 out of every 8 times. Remember that when it was shaded, we got 3 out of 8. 5 over 8 plus 3 over 8 is 8 over 8. And that's what should happen with probability. Okay, that's it for section 11.4, simplifying rational expressions. You can replay this video as many times as you like. I would also highly suggest that you read the section starting on page 664 of your book and come in with your questions tomorrow, and we'll practice some of these in class tomorrow. Have a great night.